This is Math 145, Section 5.4 notes. Now, this section's pretty dang cool. We really amp up what we're doing here in probability. Conditional probability is about saying some event has already happened. That is known to be already have happened. Now, what's the probability that some other event also will happen? So we're finding the probability of an event on the condition that some other event has already happened, right? So let's look at a couple examples there at the very top of the screen in our thought bubble. We have, think about this. What's the probability you get a sum of 5 on 2 dice? We've seen that, right? We've done that. We did that back all the way back in 5.1, in fact. But now, assume one die is 4. Does that affect the probability that the sum is 5? You betcha. That's the idea of conditional probability, okay? So we already have from a previous section that if two events are independent, right, if they don't affect one another's probability, then the probability that they both occur is equal to the probability that one occurs times the probability that the other occurs. And we use that to great effect. Now, we're going to be talking about things that are not independent. What do you think about dying from heart disease and being diabetic? Are they independent? Does having diabetes influence the probability that you die from heart disease? Well, in fact, it does. The probability of dying from heart disease is 2 to 4 times higher in a person with diabetes. That is not independent, isn't it? Okay, let's look at this definition of conditional probability here. And we have the notation, we're going to read it as probability of F given E, which is what that says. And it's the probability that F occurs given that E has already occurred. Let's look at this example down here for number 1. Consider rolling 2 6-sided dice. Here's the sample space. Answer the questions that follow. Part A. In fact, why don't you do part A and part B and pause the video here, and then we'll get back together. Okay, so here's my work for A and B. You'll notice I found the probability that the sum is 5, and I used my little notation. I want you to try to get used to that. Equals number of successes over number of possibilities, because that's what I always do for probabilities. And simply put, I counted how many successes there were. There were these that I starred. 4 of those 36 possibilities have a sum of 5, and therefore the probability is 4 out of 36, right? For part B, that's the probability that the first die is 4. Again, number of successes over number of possibilities will get me there. I circled those in red up above, and you'll notice that there are 6 successes and 36 possibilities. Therefore, I have that probability. Now, let's do part C together. Given that the first die is 4, what is the probability that the sum is 5? What are the possibilities now? How many successes are there at S? So first of all, I'm going to use my new notation. I'm going to write P of sum is 5 given first is 4. It is number of successes over number of possibilities. Now here's the cool part. What are the possibilities? Well, if I'm given that the first die is a 4, think about none of these are possibilities anymore, are they? Because the first die is not 4, right? None of these are possibilities anymore. None of these are possibilities anymore. You get where I'm going? What else is not possibilities? Those are not possibilities. The first die is not 4. Therefore, none of these are possibilities. So how many possibilities are there? There's only these 6 possibilities, isn't there? If we are given that the first die is 4, there's only 6 possibilities. And I'm going to make that my bottom. And how many successes are there? Well, there's one success where the sum is 5. And so I've got that probability there. Let's go on to the next page and see what else we have. All right, so what we were noticing there is that the first die being 4 changes the probability that the sum is 5, right? Because it essentially reduces the number of possibilities that we'll consider, right? There were not 36 possibilities anymore. If I assume the first die is 4, that means there's basically only 6 possibilities, right? And so our familiar probability of an event being the number of successes over the number of possibilities really becomes the number of possibilities are the number of outcomes that are in event E, the thing that's been given, right? And then what are the successes? How many successes are there? Well, it's those events that are in both the thing that's given and the event that we're asking about the probability of, right? So we end up here. Usually you see this in a more common form, and this is our main conditional probability formula. And it tells me that the probability of F given E has already occurred is equal to the probability that they both occur divided by the probability that E occurs alone. So let's verify this formula with number 2. We already know the probability that the sum is 5 is 4 out of 36. We found that on the last page. We know that the probability that the first die is 4 is 6 out of 36. And again, we found that on the last page. And the last thing we found on that last page was the probability that the sum is 5, given that the first die is 4, was 1/6. So I want you to pause me down and then find the probability that both of those things occur looking at the sample space. And then we're going to just check out how that formula really does work out. So pause me down, find that missing probability, and then come back. Okay, so again, I went back to my sample space, those 36 possibilities that I had listed on the last page. And in fact, I was looking for the outcomes that had a sum of 5 and the first die is a 4. And it turned out that there's only one outcome of that description, and that's that 4, 1. And so I have the probability that the sum is 5 and the first is a 4 is 1 out of 36. And again, that's just number of successes over number of possibilities. So let's wrap this question up. It tells me, now notice that probability that the sum is 5, given that the first is a 4, is equal to blah, 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 blah. Now, really all I'm doing is using that formula. It says, fill out that equation with the appropriate probabilities to verify it. So, and we can do our fraction math on a calculator if we need to. So essentially, here is what I want you to see. The left part of that equation is that 1/6, right? And again, that was the probability that we found at the bottom of the last page. And my formula tells me that this should be equal to, and I'm just going to put a question mark over there. I'm not taking it for granted yet. I'm just putting a question mark. Let's see. So it should be equal to the probability that the sum is 5 and the first is 4. Well, that was 1 out of 36 that I just calculated over there in red, divided by the probability that the first is a 4. And again, that was up here. And you'll remember that was, I have 6 over 36. You know what? I'm going to go ahead and write it that way. Now, what I can do to verify this, right, is I simplify the right-hand side and see if it really does actually equal 1/6. So I'm going to do fraction math by hand. I remember that dividing two fractions is done by if I take the first fraction as is, the top fraction as is, and then flip and multiply the second fraction on. So you notice I do that. Oh, hey, look at that. That really is 1/6. Yay! It really did equal 1/6. So again, we're just in our mind trying to stack up the evidence that this equation really does work. Now you'll notice if I take this equation that I just circled up here, this big crazy big circle, if I take that equation and I just multiply both sides by P of E, I get down here. It's just an alternative way you might see this rule. And it's nice to see because, as it says here in the notes, this has probability of E and F isolated on the left-hand side. And it just reminds me of that same probability of E and F formula I have. But remember, this is for independent events here. And essentially, we have the not independent events here. Okay, so that's that. Let's move on. All right, we've seen some contingency tables a little bit earlier. We're going to see them again, obviously, here. Look over number 3, and why don't you answer A, and then we'll talk about the rest of them together. Go ahead and read over the data and pause me here, and then we'll meet up again. Okay, so what we've got here is the marital status of males and females 15 years and older in the U.S. in 2013. So we've got marital status broken down, right? And I've got males here, females here, the total here. You'll notice I found the totals in both the row totals and the column totals. That may or may not have been done in your contingency table that you're given, so you always want to do that. Part A says, what is the total number of males? And I wrote down from my table there, 122.5. Make sure you write in that million part there. That's quite important, isn't it? Now, Part B says, find the probability that a person selected at random would be widowed given that they're male. And I'm going to write it like that. So here's what we're going to do. As always, right? Number of successes over number of possibilities. Simply put, the number of possibilities is not the total 251.3 million because we are given that the person is a male. We know that this person came out of the 122.5 million, right? You could put million on there if you wanted. Now, how many successes are there? What we're looking for are of those males, the ones that are widowed. Right, let's find that in our table. What is that? Looks like here, 3.1. Yeah, so then that's going to go on top. Right? And if you wanted to, you could cancel out those millions. You could write it as 3.1 over 122.5 or simply get the decimal equivalent, which I did, and I got 0.025. Okay, let's go on with letter C. In fact, why don't you go ahead and do letter C, pause me here, and then we'll meet up again after you try out letter C. So for part C, we wanted to find the probability that a person selected at random would be male, given that the person is widowed. I wrote that like this. And then I'm going to think about number of successes over number of possibilities. Well, how many possibilities are we looking at? Let's see. We are given that the person is widowed, right? So we need to have the total number of widows. That's 14.3 on the bottom. How many successes? How many males are also widowed? Well, wasn't that 3.1 we had? Now, if you do that calculation, you're going to get about 0.217. And if you want to think about that as 21.7%, you absolutely could. We're saying that 21.7% of all widows are male. That's a good thing to know. D tells you to return to questions B and C to write a sentence for each that helps show the difference between what you found. Again, I just kind of said what I kind of want to do there for C. So I'm going to write 21. Shoot, sorry, it's hard to write on this pen in certain locations. 21.7% of widows are male. That is what that means, right? Let's come up here. First of all, for letter B rather, 2.5%, right, is the percentage equivalent. So here what we're saying is 2.5% of what? Think about this. The total, we're not widows, but males. We're going to say 2.5% of males are widowed. Different, isn't it, than what we had done in Part C? See the difference? All right, let's move on. Number 4 here has to do with exploring a little bit so that we can see this rule that we have down here at the very bottom of the page. So why don't you do A and B, and why don't you even take a look at C and then pause me here and then, come back to me. All right, so what I did was I found for Part A, the probability that a randomly selected person is separated. Notice there was no given such and such. This is not a conditional probability. This is simply a straightforward probability where the number of possibilities is every single person in that data. And the probability of being separated is, as we always say, number of successes over number of possibilities. Number of successes being these 5.6 separated people out of the total, right? Which, rounding to the nearest whole percent, is 0.02, which again is 2%. All right, now Part B. Here we were given that the person is male. So we're finding the probability that a randomly selected person is separated given that they're male. Again, using my conditional probability formula, or my conditional probability write-up. I have number of successes over number of possibilities, but here the number of successes is 122.5, because we are assuming, because we're given that they're male, that they are in this group, right? And then we count how many are separated in that male group, and that's at 2.4. And so we divide the two, and you get 0.02, which is, again, 2%. Now, Part C says, notice these two, as they are rounded, probabilities are equal. What do you think that means about the events separated in male? Let's think about this. The probability of being separated is essentially equal to the probability of being separated, given that you're male. Notice that this essentially is telling us that the fact that it was given that they're male did not affect the probability of being separated, right? The probability of being separated, flat out, as we found in Part A, is equal to the probability of being separated given that you're male in Part B. So it must mean being male does not affect that probability. Well, what does that mean? Doesn't that mean independence? Isn't that what we're talking about when we're saying, does something affect something else? And so we have a rule at the bottom of page 4. And you can think of it as an extension to the definition of independent events. It basically says if two events are independent, then you have this relationship. Probability of E given F is just equal to the probability of E. And if you know this probability is true, if you know the probability of E given F is equal to the probability of E, then you can assume that the two events are independent. So in conclusion, on number 4, we are going to conclude that separated, I know I spelled that wrong, and male are independent events. Let's try to put an A in there. Okay, perfect. Let's move on. Go ahead and read over number 5. See if you can make sense of it. Maybe see if you can think about how the notation applies to these events that they're talking about here. And pause me, and then we'll meet up again. Okay, so first of all, I looked at the question. What is the probability that a randomly selected death is the result of cancer if the individual is known to have been 25 to 34 years old? That sounded like a conditional probability. And so I use my conditional probability notation there. I have the probability of cancer given that the death is of a 25 to 34-year-old. And again, I don't know that, right? Now, look at the first two sentences and you get the bits of information that you need. You just need to know what you're looking at, though. So the first sentence, according to the U.S. National Center of Health Statistics, 0.15% of deaths in the U.S. are 25 to 34-year-olds whose cause of death is cancer. Isn't that an implied and? So first of all, I see two events here. One event is death is caused by cancer. One event is the death is of a 25 to 34-year-old, right? This 0.15% of deaths is the probability that a death is a 25 to 34-year-old and they died from cancer, right? And then that second sentence, in addition, 1.71% of all those who die are 25 to 34-year-olds. That tells us that the probability of death is of a 25 to 34-year-old is 1.71%. So look at what you're dealing with. You've basically got this formula. And what I want to know is the probability that their cancer, given that the death is 25 to 34-year-old, I am abbreviating a bit, that's equal to the probability, here I'm going to use this formula without rewriting it. I'm going to say the probability that they both occur, which is at 0.15%, I don't need to write that down, and divided by the probability that the death is of a 25 to 34-year-old, it's 1.71%. Let's go ahead and get an answer for that. Looks like it's about 0.09%. Okay. Let's look at number 6. Suppose that a computer chip company has just shipped 5,000 computer chips to a computer company. Unfortunately, 30 of them are defective. Part A says compute the probability that 2 randomly selected chips are defective using conditional probability. All right, so here's what we're going to think about. I'm going to say, first of all, first chip defective and second chip defective. That is what we want, right? They've got a box of 5,000 computer chips. They're going to pick out 2 randomly selected chips. We want to know the probability that they're both defective, right? Well, that's equal to the probability, using conditional probability, of the first being defective times the probability that the second is defective, given that the first was defective. Now, I am using this formula up here. I'll write it in red down here. I am using this probability, that the probability of E and F is equal to the probability of E times the probability of F given E. If you think about how this is actually working out, right? What's really happening in real life, right? They're taking out a chip, they're seeing if it's defective. Let's assume it is defective. Now, of course, it would not get put back in the box, right? It would get maybe put on a work table to be looked at later. And then they'd put out a second chip and see if that was defective. Now let's think about what are those probabilities. Well, at the first chip, they have a box of 5,000 chips, and 30 of them are successes in that they would be defective, isn't it? So the probability that the first is defective would just be 30 over 5,000, wouldn't it? Now, again, we're going to assume the first was defective. So the first was defective, pulled out of the box, defective, and then put aside somewhere, right? What's the probability that the second one is also defective? Well, probability is number of successes over number of possibilities, and number of possibilities is now 4,999, isn't it? Because there's one of those 5,000 chips that's over there on the work table, right? The first one we picked out. Well, how many successes are left? Again, being success being the second one is defective, right? Well, we pulled out a defective one because we were assuming that, right? And so there should only be 29 defective ones left, shouldn't there? And so we've got that probability. And if you're on MyMathLab, you might need to write it as this. This is how the calculator gives it to me in scientific notation. So technically the calculator really gave me 3.448e negative 5. Some other stuff in there. But that's what that means. A very, very small number, isn't it? Okay, let's do B. B assumes they're independent, so we're just going to talk about the first being defective and the second being defective. Equals, if these are independent, then I can multiply those probabilities, can't I? Now again, we're not thinking about conditional probability, we're just thinking about what's the probability the first is defective? Well, there's 30 over 5,000, right? Probability the second is defective, it's 30 over 5,000 again. Now when we get that calculated, we're going to end up with 3.6. Actually, this is not approximate. This is an exact 3.6 times 10 to the negative 5. And you'll notice part C actually asks you this question. What can you say about these two probabilities? Well, they're very close, aren't they? We got 3.48 times 10 to the negative 5 up here in part A, and 3.6 times 10 to the negative 5 down here in part B. Very, very close. In fact, there's kind of a point here. And it goes like this. If a small random sample is taken from a large population without replacement, which you're assuming is the situation here with these computer chips, right? You wouldn't take out a chip, test it, and then put it back in the box. It is reasonable to assume independence of the events. If n, the sample size, right? Sample size, in this case, n is 2 for our 2 chips we were picking out. It's less than 5% of capital N, we assume independence. And so we can basically say we can use this method of finding the probabilities and not have to assume conditional probability. That also reminded me that I forgot to mention on number 5 question this, would this be unusual? Since this probability is less than 0.05, it is unusual. Sorry, I forgot to mention that this probability that we found up here in number 4, I'm sorry, excuse me, in number 5 being 0.0009, comparing that to that, or comparing 0.09% to 5% is just another way to think about it. Okay, so we would say that, thankfully, the probability that a person has died from cancer, given that they're 25 to 34-year-olds, is unusual. Okay, read over number 7. Try to write out the sample space as they say, and then we'll get back together. Pause me here, of course, and we'll get back together and we'll do that tree diagram that they want. Okay, so again, we are kind of thinking about this box of computer chips. There are 5,000 computer chips in a box. 30 of them are defective. The computer company is going to randomly test 2 chips out of every shipment. If both chips work, they will accept the shipment. If one or both tested chips are defective, they will reject the shipment. So we know what it takes for them to reject the shipment. Use a tree diagram, it says, with conditional probability to organize the possibilities and probabilities for these 2 chips. What is the probability that the shipment will be rejected? Now let's think about, again, that means one or both chips are defective, right? And then we'll also answer the question, is that unusual? Is it less than 5%? Okay, now I asked you to do your sample space. Did you get this? Did you get, for the sample space, D for defective, G for good, these 4 possibilities? Both defective, both good, First one's defective, but the second one's good. And the first one's good and the second one's bad. All right, good. So let's see about this tree diagram. First, we picture ourselves reaching into the box, pulling out a chip, right? Well, there's two possibilities for that chip. By the way, I suggest you start your tree diagram as far left as you can and in the middle of this large space that you're given. So I am going to start about here, and I'm going to say my first chip was either good or bad. So it was good or defective. And again, this is the first chip. Okay. Now, what are the probabilities of those things? Okay, well, the probability that it was good was 5,000 total. And how many good? Well, 30 of them were bad. So 4,970 were good, weren't they? Defective, 30 out of 5,000. Now, let's go on. Think about our second chip, right? So again, the idea is our first chip was chosen. Let's say it's good. We're going to follow the fact that it's good here. Now, we're going to think about our second chip. This is our second chip here. Well, it's either good or defective. Now, let's think about the probability of those. And this is where conditional probability really plays a role. So, again, probability of G and D are both number of successes over number of possibilities. It's just a matter of how many of each you have, right? So, assuming the first chip was good, we are on that branch of the tree. We have to assume the first chip was good, okay? Then we're going to come up here and say, what's the probability that the second chip was also good? Well, number of successes will, assuming that the first chip was good, the number of successes should go down by one, shouldn't it? Shouldn't it be 4,969 successes left, since the first one was also good? And how many possibilities? Well, wouldn't there be one less possibility of there too? Let's think about defective. What's the probability that that one's defective? Again, think about number of successes over number of possibilities. Number of possibilities is 4,999. How many successes are there? When again, a success isn't now being defective, right? So if the first one was good, how many successes are left for the second one to be defective? Well, there's 30 defective ones left, isn't there? So we got that. Let's go on to the other branch of our tree. So essentially that first branch of the tree accounted for the first one being good, and then broke off to and the second one's good or bad, right? So now we go to the second branch of the tree, which is assume the first one is defective, bad, right? Now what's happening to the second one? Well, the second chip could still be good or defective. Let's think about the probabilities of those. Again, we have to assume now the first one is defective. So what's the probability that the second one is good? Well, first of all, there's 4,999 possibilities left, right? Because that first chip is gone. The first chip was defective. So one of the defective chips is gone, leaving me, as far as how many good ones there are, 4,970 of those, yeah? And then let's look at this last bit. So assuming the first one was defective, what's the probability that the second is defective as well? Okay, well, number of possibilities, still 4,999, because again, the first chip has been taken out, so there's one less than 5,000 chips in the box at the time we pick the second one. Now, how many successes are there if a success is being defective? But I'm assuming that the first one was defective. So one of these 30 successes is gone. So now there's only 29 successes there, isn't there? And it turns out, and this is really super cool, that you can find these probabilities. Say the probability of GG, meaning the first one's G and the second one's G, by multiplying these probabilities together. So if I take that times this, I will get the probability that the first one's G, good, and the second one's G. Okay? And of course, you could do that for each one of these. You can find the probability of GD here. This string will find the probability of DG. Here's the probability of DD. There is an alternative way of finding the probability here that we're after. Now, let's go back to the question itself. And it says, let me get some red there. So, and it says, what's the probability that the shipment will be rejected? One or both chips are defective. Okay, well, what is that? That's GD, DG, and DD. I need to add these. I need to add these probabilities, and then I'll get the answer to that. You can do that real quick, and then I'm going to do it too, and we'll see what we get. And then we'll answer the question, is that unusual? Okay, I had to add another little slide in here to just show that this worked for that. This is the probability that the shipment is rejected, which is, as we talked about, there's 3 outcomes in that sample space where they reject the shipment. And that is the first one's good and the second one's defective, or the first one's defective and the second one's good, or they're both defective, right? So since these were mutually exclusive, they cannot happen at the same time, right? Then I can say the probability of this or that or this is equal to the probabilities individually and add it up. And that was, we got from a previous section, 5.2. And then the next thing I did was I found these individual probabilities. But as I say, these really did just come from the tree diagram. So that wasn't too rough. I multiplied those together on the calculators, and of course I came up with decimal equivalents and added them up. Looked like that last one didn't amount to much, and so it ended up being the probability is 0.012, or 1.2% of the time the shipment will be rejected. And it asked me, is that unusual? And remember that it's not, it is less than 5%. So yes, it's unusual, which is good because you don't want it to be usual that you'd have to reject your shipment, right? Okay, this one is here to talk about this idea of with or without replacement. So why don't you go ahead and read this over, read over A, maybe see if you can do A and maybe even B. See what you can do. Pause me and come back to me. All right, so as it says, it doesn't make sense to take a computer chip out, test it, and then put it back in the box so that it could possibly be checked again, right? So that problem did not have replacement. It was without replacement. But of course, there are applications like picking cards out of a deck or playing songs off of the song list where, in fact, you could play a song and then play it 3 songs later, right? That's a possibility. That is with replacement. Number 8 gives us an example of this. It's very similar to, by the way, one of your homework problems. It says number 8, you listen to an album which has 12 songs. You like 4 of them. Answer the following questions. A, if your music player plays 2 songs at random, what is the probability that you will like both of them? Let's write this as the probability of like both. But then let's rewrite that as like first and like second. Now, his is big. Assume the first song cannot be played again. So, what is this probability? Because the probabilities will change because you're not basically replacing this first song that you play back into the playlist in order to possibly be played again. You're going to have to assume conditional probability. Can you write down what this probability would be equal to using conditional probability? Pause me now and see if you can. Okay, now this is how I set it up. Notice I have the probability that I like the first times the probability I like the second, given that I like the first. Notice that it would not have been okay to switch the order in those, because I can't find the probability that I like the first, given that I like the second, because the second hasn't happened yet when I'm liking the first. So I cannot switch the order. Make sure you've got it in that order. Now let's actually look at it and think about what's actually happening as it's coming out, right? The first song comes out. What's the probability I like it? Well, number of successes over number of possibilities, right? Always number of successes over number of possibilities. It's a matter of counting up those, right? Well, there's 4 successes over 12 possibilities, wasn't there? Now, what's the probability I like the second, given that I like the first, is the next probability I'm after. I cannot play that first song again. Now then, how many possibilities are there for songs when you play the second song? There's no longer 12, is there? There's only 11 songs. And what's the probability I like it? Well, how many successes are there? Knowing that I liked the first one, right? And again, that's this part of this probability that we're looking at. Knowing that the first one was liked, one of those 4 songs that I like was already played and out there, and gone. So how many successes are left? That would be 3, wouldn't it? Well, that's 12 over 12 times 11, and that's 1 over 11, isn't it? And if you wanted to, I think you get that out. I think that's 0.09, isn't it? Yeah. So if you wanted to get a decimal out, you could. Let's look at B. If your music player plays 2 songs at random, what's the probability you will like both of them? Assume the first song can be played again. So this is, again, with replacement. So we've got the probability that I like the first and like the second. But since the first song is going to be put back into the pool again to possibly be picked again, we don't have to worry about conditional probability. These are independent, aren't they? If you replace the first song, then you can say liking the first and liking the second are independent. So liking the first is 4 out of 12. Liking the second one is still 4 out of 12, isn't it? What is that, 16 over 144? It looks like, what is that, 1/9? Okay, letter C. If your music player plays 2 songs at random, what's the probability that you will like neither of them? Think about that. What do you think about that one? Pause me and see what you think on your own. Okay, part C. What's the probability I'll like neither of them? This is how I thought about it. This is the probability of not liking first and not liking second, right? Since, again, the first song can be played again, this means they're independent. So I can simply say that's equal to the product of the probability of not liking the first times not liking the second. Probability of not liking the second, right? Since not liking it has 8 successes and 12 possibilities, 8 over 12 is the probability for that. Same thing for not liking the second one, because again, the first song is being put back in, and so the pool doesn't change. It's still 12 songs with 8 successes. Here, again, successes being not liking it, right? And if you multiply 8 12s times 8 12s, you get 0.44. Let's look at letter D. Read that over. You'll also see there's a little hint in this thought bubble here. So pause me and come back. Here's what I did. I thought about what does it mean to like exactly one song. You'll also notice I'm assuming the first song can be played again, which is the same assumption we've been making all along through B, C, and D. Okay, now, liking exactly one song. What does that mean? All right, well, I actually have here a little table that I made up, just simply the possibilities that can occur in this experiment, right? So number 1 is I can like song 1 and song 2. Number 2, I can not like them both. Number 3 option, I can not like one but like number 2. And number 4 option, I can like number 1 and not like number 2. You'll notice that we basically have found the probability of like in part B. We found the probability that we don't like both in part C. I want you to notice that part D is really these two options, right? That you not like the first and like the second, or not like the second but like the first, right? These are the options in part D. So I want to know those probabilities. Well, wait. I know the probabilities of each and every one of these four things happening is the sum of those probabilities is equal to 1, right? So shouldn't I be able to take the probability that I like exactly one song and make it equal to 1 minus the probability that I like both minus the probability that I not like both? Which is 1 minus the probability that I like both, which was that 0.11 that we found in part B, minus 0.44 that we found in part C, which makes 0.45, it looks like. That is the probability that I like exactly one song. That was not the only way we could have done that part D, but it was probably a little bit, probably the easiest way.